Welcome to the next lecture on ARPIT on the course Introduction to Quantum Physics and its Applications. So far we have discussed about one-dimensional harmonic oscillator and few higher dimensional problems, for example, two-dimensional and three-dimensional infinite potential well, where we also discuss about how the concept of degeneracies come into picture in the higher dimensional problem. So today what I am going to do is to show you some problems, how can we solve some of the problems on these two topics, the harmonic oscillator and higher dimensional problems, how the degeneracies can be calculated and so on. So we will solve 5 problems in today's lecture on these two topics. So let us first recapitulate a couple of concepts that we learnt in the previous class. So what we learned in the previous class is how can we solve a one-dimensional harmonic oscillator problem. We have not really analytically solved this problem, but I showed how different solution, different wave functions and the energy eigenvalues for this problem looks like. Because in order to solve the Schrodinger equation for this particular case, one really has to apply a more advanced mathematical procedure which is called Frobenius method. So more details will come into the lecture notes. What I have shown is how the different wave functions and the energy eigenvalues look like in this particular case. We have also discussed the higher dimensional problems like a two-dimensional infinite potential well and three-dimensional infinite potential well, and introduced the concept of degeneracies. So let us quickly look at the one-dimensional harmonic oscillator problem. So as you all know, a harmonic oscillator problem is really governed by a potential half m omega square x square, or its or other way of writing this is half k x squared. So the Schrodinger equation in this case looks like this: d2 phi dx squared plus 2m over h cross squared e minus half kx square phi is equal to 0. And in general, the solution for such differential equation can be written in this form: phi n equal to a n, which is some constant, fn alpha x e to the power minus alpha x squared, where these alphas are related with mass and omega, which we have already shown an expression for. Now this fn is actually a function of x, and it governs a special kind of differential equation which is very well known as Hermite differential equation. And the energy eigenvalues in this case is given by En equal to n plus half h cross omega, where n goes from 0, 1, 2 and so on, takes on integer values. The other interesting thing is that even in this particular case of 1D harmonic oscillator, there are classically forbidden region which intuitively we can't expect the particle to have an axis, but quantum mechanically there are some probability of finding the particle in this region as well. The wave function in this region goes decay exponentially, and we will look at some of the schematic diagram of the wave function in the next slide. So as I said, this fn of alpha x are actually a solution of Hermite differential equation, and the first 4 polynomials for n equal to 0, 1, 2, 3 are given by these expressions. So the so one can actually construct the ground state, first excited state, second excited state wave functions for this harmonic oscillator problem for n equal to 0, 1, 2 and so on. So if I quickly show you the wave functions and the probability density, which is the mod square of the wave function, are shown in this diagram. They actually, as I said, have a Gaussian type of behavior inside the well, and as it goes outside the well, it actually decays exponentially. So the lowest one is phi 0x, corresponding to the energy eigen value half h cross omega, and it looks like this as shown by the blue line. The first excited state has 2 nodes in it, as you can see, but as soon as it comes out of the well, it actually decay. The phi 2x has 3 different points where it goes either a maxima or a minima, and as we actually go to higher and higher states, the number of nodes actually increases, and as you come out of the well, it once again has to decay exponentially. But the interesting thing is that even outside the quantum well, you do have certain probability of finding the particle in this case as well. Okay, so then we also discuss about three-dimensional infinite potential well, and the differential equation in this case, of course, looks like this: del square phi plus 2m by h cross square e minus v equal to 0. The three-dimensional infinite potential well can be imagined as if a particle constrained to move inside a cube, or each of edge length L, and the potential inside is 0, and outside this cube is infinity. So one can solve the Schrodinger equation inside this cube, where the V potential is equal to 0, and one can actually apply something called the method of separation of variables to solve the differential equation, the three-dimensional differential equation, and can find 3 distinct differential equation for each of x, y, and z variable. The energy eigenvalue in this case looks like this: E equal to pi square h cross square divided by 2ml square into nx squared plus ny squared plus nz square. So you can notice that unlike the one-dimensional infinite potential well, where there was only one quantum number and the energy eigenvalue was in the form n squared pi squared h cross squared by 2ml squared, in this case there are 3 distinct quantum numbers denoted by nx, ny, and nz, which controls the values of the energy depending on the value of these nx, ny, and nz. Similarly, the wave function also is characterized by these 3 quantum numbers, and the form of the wave function is this, which is 2 over L 3 by 2 into sine n x pi x by L, n y pi y by L, and sine n z pi z by L. Okay, so we also discussed about the degeneracies in a three-dimensional box. What is the degeneracy? Degeneracy basically is a concept where depending on a certain combination of values of nx, ny, and nz, if we get the same value of energy which corresponds to different form of the wave functions for each combination of nx, and y, and z. Let us look at closely. So for example, if I take a value nx equal to 1, ny equal to 1, and nz equal to 1, which is the first row in this table, then my n squared, which is the sum of nx squared plus ny squared plus nz squared, will take a value 3. And there is only a unique wave function for this particular case, which is phi 1 1 1. However, there are other combination of nx and y and z such as 1 1 2, which is the second row in this table, 1 2 1 or 2 1 1. All of these combinations will give me the same energy. So n squared value is going to take a value 6 in all these 3 cases. However, if you substitute these values of nx and y and z in the wave function, you will actually get 3 distinct wave functions for each of these combinations. So although these 3 distinct wave functions are different from each other, but they correspond to the same value of the energy, which is 6 in this case, rather 6 into pi squared h cross square by 2ml square. Similarly, there are a plethora of other combination of nx and y and z which will give rise to different fold degeneracies. We have also discussed about something called asymmetric potential, or how the degeneracies for a given problem can be lifted. What does lifting of degeneracy means? So this is a very simple example. What I have done here is basically I have modified the cube into a rectangular parallelepiped form, which means I made one of the edge length of this cube different compared to the other two. So here in this case, the edge length along x direction is L1, but the edge length along y and z directions are same, which is capital L. And definitely for this particular geometry, my energy eigenvalue is going to change, and it will have a form as given here: pi squared h cross squared by 2m, nx squared by L1 squared plus ny squared by L squared plus nz squared by L squared. Similarly, my wave function will also get modified, and it will have this particular form, and it is a normalized wave function because I have already calculated the normalization constant, which is 8 by L squared L1 to the half. Now, in this particular case, as we saw in the previous case, the 1, 1, 2, 1, 2, 1 and 2, 1, 1 were three-fold degenerate states, because each of these combination of nx and y and z gave me the same value of energy but different eigenstates. In this particular case, these three combination will actually not give same energy in all the three cases. So you can easily notice, if I take nx and y and z values to be 1, 2, 1 and 1, 1, 2, then the energy that I will get from this expression will be same. However, the 2, 1, 1 combination of nx and y and z will give me a different energy, which means that the threefold degeneracy that I got in the cubic case is now lifted, and it actually split into two different degenerate cases. One is two-fold degenerate, the other one is non-degenerate. So the threefold degeneracy is lifted to two-fold degeneracy in this particular case. This has a much broader way of looking at it. In general, this was a very simple example, but in general, the more symmetric the system is, the higher the degeneracy I can get in any quantum mechanical system. And as soon as I break the symmetry, or as soon as I go to a more asymmetric cases, the degeneracy is going to be lifted, and I will have more non-degenerate states as compared to the states in the symmetric cases. So this is in general true. Any quantum mechanical system, the more symmetric the system is, the higher the degenerate states I will get. Alright, so having learned some of these concepts and ideas, what I will do now is to discuss few problems and solve them, so that you can get a better idea how can one look at the degeneracy, the harmonic oscillator problems in general. So this is problem number 1, and I'll just quickly read it. So this is basically a problem where a charged particle of mass m and charge q is bound in a one-dimensional simple harmonic oscillator potential of angular frequency omega. An electric field E0 is turned on. So this is a problem where, of course, I have a one-dimensional harmonic oscillator, but this particle is a charged particle, and it is under an additional potential created by this electric field E0. And what we want to calculate is what is the total potential that the particle will experience in this case, and can we actually express this total potential in an effective harmonic oscillator potential form. How does the potential look like if I want to sketch it? What is the ground state of the particle in this case, and what is the expectation value of the position x if the charge is in its ground state? So as I said, this is a problem where there is a harmonic oscillator, but it is under the influence of a charged particle. So let us look at how can we solve this problem. Okay, so the first question was, what is the potential, total potential that the particle will experience in this case? So definitely, because this particle is in a harmonic oscillator potential well, there will be a term half m omega squared x squared, which we have already learned. But due to the electric field, because this is a charged particle and there is an electric field which is turned on, there will be an extra potential that the particle will experience, which is minus q times E0 times x, where q is the charge of the particle and E0 is the electric field which is turned on. So, the total potential that the particle will experience here will be half m omega square x squared minus q e 0 x. Now, if someone asks me to solve this problem, solve the Schrodinger equation using this potential well, one can go ahead and solve this by conventional method. But the question is, can we still use a trick to solve this problem without much of a mathematical complication? So, the question in the part B is to facilitate that particular trick. So, what we do here, as you can see that I have actually tried to rewrite this potential form in a complete squared form, and there is a reason behind that. So, as you can see that I have just taken half m omega squared common from here, and eventually I wrote it as a x minus q e 0 by m omega squared whole squared. Okay. And then there is a term which is independent of x, which is like a constant scalar. So, this potential can actually be visualized as if this is a displaced harmonic oscillator potential displaced by x equal to q e 0 by m omega squared, and then there is a shift in the potential value. So, this is what I have sketched here. So, as it stands, this potential well has a different minima now, which is at x equal to q e 0 by m omega squared, and it actually has a constant shift. So, at x equal to 0, it has a particular value, and at x equal to 0, it is actually 0, which actually is obvious from this particular expression, because if I substitute x equal to 0 in A, then potential is 0, but then the minima is shifted here, which is at x equal to q is 0 by m omega squared, and the value of the potential at the minima is a different value, which is shown in this graph. So, it is still a parabola, but it is a displaced or a shifted parabola, and by plotting this sketch I assume that q e 0 is greater than 0. So, this is the third part of this problem. The fourth part of this problem was, what will be the ground state energy of the particle in this particular potential. So, the ground state energy of the particle in this potential can be calculated from this particular expression, because as I said that this particular expression is still a harmonic oscillator potential, but with a constant shift. So, half m omega squared x minus q e 0 by m omega square whole square, it still looks like a harmonic oscillator, but with some constant shift. So, I will still have the ground state energy to be the same as a harmonic oscillator, which is half h cross omega, as I have written here. But then there will be a shift in the overall energy scale, which is given by half q is 0 by m omega squared whole squared into m omega squared, which is nothing but this scalar value which is there in this potential expression. So, the ground state energy is this, and in general the nth state energy for this particular problem can be written as this n plus half h cross omega minus this scalar factor. So, you should realize that we have bypassed solving this full potential problem by solving the Schrodinger equation from beginning, but we just scaled this potential, rewrite in a modified harmonic oscillator form, and calculated the energy eigenvalues like this. The next question was, what is the expectation value of the position x if the charge is in the ground state? Now, by symmetry, as we have already discussed in the previous lecture, the expectation value of the position is actually 0 in this case by symmetry. So, which means in this particular case the expectation value x minus q e 0 by m omega squared is actually 0, because the integral for any general nth harmonic oscillator state, the integral of psi n x star x times psi nx, this is actually always 0. So in this problem, it is the expectation value of x minus q is 0 by m omega square is 0, which implies that the expectation value of x will be q is 0 by m omega square. So in this particular case, the expectation value of the position x has a particular value given by this expression. Okay. Now let's move on to the second problem. Now this is also a very interesting problem where the concept of superposition is being used. So what is this problem? It says a particle of mass m is confined to move in a potential half m omega square x square, which is a simple harmonic oscillator potential, and at a time its normalized wave function is given in this form, where beta is a constant of appropriate dimension. What we need to calculate is the expression for beta in terms of m omega and h cross. Then what is the probability of observing the particle in the ground state, or rather the lowest energy eigenstate. Okay, because the wave function which is given is actually in some kind of superposed state, although it is normalized. The third question is, it can be shown that the above wave function is the linear combination this. So it is given that if this wave function can be written in a linear combination of psi 0 ground state and psi 2 second excited state, then the question that is asked is evaluate the value of B and hence calculate the expectation value of the energy of the particle in this state psi x. Okay. So let us quickly see how can we solve this problem. So the first question was obtain a dimensional expression for beta in terms of m omega and h cross. Okay. Now as if I go back to this expression, the psi x, this has a beta in the exponential also, so e to the power minus beta x squared by 2, which clearly says that beta has a dimension of L to the power minus 2, where L is the length dimension. So beta has a dimension L to the minus 2. Now it is known that m omega squared x squared by 2 and h cross omega by 2 both have the dimension of energy, because you have seen that half h cross omega, 3 by 2 h cross omega are the energy eigenvalues for this harmonic oscillator problem. So both of these half m omega square x squared and h cross omega by 2 have the energy dimension, which means that h cross omega divided by m omega squared x squared is dimensionless if you just take the ratio of these two energetics. This implies that m omega squared by h cross omega is equal to m omega by h cross has the dimension of L to the power minus 2, because there is x squared in the denominator. Therefore beta should have the form m omega by h cross by this simple dimensional analysis. Okay. So let's move on to the second part. The second part asked what is the probability of observing the particle in the ground state for this particular wave function psi x equal to this one which is given here. So this is something which we learned before also, that if a particle remains in a mixed state psi x, then the probability of finding the particle in a given state, say ground state or first excited state or second excited state, can be calculated from this expression. So the amplitude for observing the particle in the ground state is this. This is in general true. For the ground state, this is psi 0 x times psi x dx, where psi x is the superposed wave function in which the particle is. But if you multiply it by psi 0 x, this will give you the probability or the amplitude of finding the particle in the ground state. If you want to find the probability in say nth state of the problem, then you multiply psi x by psi nx and then integrate over all space. That will give you the amplitude of observing the particle in the nth state in general. Okay. Now for this particular problem, in the slide where the actual problem was given, this spatial integral has to be given, because that will ease out the evaluation of this integral, and also the ground state wave function for this problem also needs to be given. So, the ground state wave function for the harmonic oscillator potential well is psi 0 x equal to beta divided by pi to the 1/4 e to the minus beta x squared by 2. So, if I substitute this value of psi 0 x in this particular integral, and also use this form of the wave function psi x to be a constant times x squared e to the minus beta x squared by 2, I will get an integral of the form integral minus infinity to plus infinity x squared e to the power minus beta x squared dx. Now, there are standard integrals to evaluate such integration, and the spatial integrals has this form as shown in the right box, and if you use that, you will get the value of this the amplitude of this observing the particle in the ground state to be 1 over root 3, and hence the probability of observing the particle in the ground state will be the mod a squared, which is 1 over 3. What does this mean? This means that if a particle is in a superposed state as given here, then if a measurement is done on the particle which remains in this mixed state, and if a measurement is done, the 1/3 of the time you will find the particle to be in the ground state and 2/3 in some other state. What is that other state is something which is the third question here, that it can be shown that the above wave function is the linear combination of the ground state and the second excited state, that is psi 0 and psi 2, and the question that is asked is evaluate the value of B and hence calculate the expectation value of energy. So, let us see. If I come to problem number C, it is given that my total wave function psi is written as a linear combination of psi 0 and psi 2. Now, where psi 0 and psi 2 are all normalized states. Now, I have already seen in the previous problem number B that the probability of finding the particle in the ground state is 1/3, which means a squared is already 1/3, because as you know from the principle of superposition, if I write a wave function psi in a linear combination of different eigenstates, then their coefficient square gives me the probability of finding the particle in that particular state. So, a square plus b square is equal to 1 will imply b square to the power to be 2/3, because a squared is 1/3 as we have seen in the previous problem. So, b is root 2 by 3 in this particular case. And the second question which is asked is what is the expectation value of the energy. So, the expectation value of energy will simply be probability of the ground state multiplied by half h cross omega. Sorry, it looks like half h cross omega is on the up, but it is nothing but multiplication of probability of the ground state multiplied by half h cross omega plus probability of the second excited state multiplied by 5 by 2 h cross omega, because 5 by 2 h cross omega is the energy of the second excited state and half h cross omega is the energy of the first excited state. Now, we have already calculated the probability of ground state and the second excited state, which are 1/3 and 2/3 respectively. So, if you substitute that value here, it will eventually give you the total expectation value of the energy to be 11 by 6 h cross omega. So, the take home message of this particular problem is that, and there will be some problems in the tutorial sheet to you, where instead of the wave function to be in this form, I will give you some problem where the wave function will be in some other form, which of course is a mixed state, and I will call different question like the probability of finding the particle in the first excited state, or in third excited states and so on. So, there will be similar problems of this kind in the tutorial sheet, except that you will have a different function psi x as opposed to this one. So, that should be a straightforward calculations, and again these special integral will be useful to evaluate these integrals for the probability. Okay, moving on, let us move on to the third problem. So this problem 3 is actually a combination of a harmonic oscillator and an infinite potential well. So you can see here that if I look at the potential at x equal to 0, it has a infinitely high wall, which is similar to the infinite one-dimensional potential well. However, the difference here is that on the right hand side, instead of the wall to go to all the way to infinity, I have made it a harmonic oscillator. So for x less than equal to 0, it is like an infinite one-dimensional potential well, but x greater than 0, it is a harmonic oscillator. So this is also sometimes termed as half harmonic oscillator potential. And the question that we would like to answer is, what is the ground state wave function for this particular problem, and what is the ground state energy for this? So let us see. So as we have learned in some of the previous slides, that in general the wave function for a harmonic oscillator potential well, for a full harmonic oscillator potential well, where both sides x less than 0 and x greater than 0 was harmonic oscillator, the wave function in general has this form: phi nx equal to an fn alpha x e to the power minus alpha x squared. And the energy eigenvalues have this form: En equal to n plus half h cross omega, where n can take values 0, 1, 2, 3 and so on. And these f of n x are basically Hermite polynomials. First 4 of them are listed here. Now, the most important thing that one need to keep in mind in order to find out the wave function for this problem is that because of the infinitely high wall at x equal to 0, one need to satisfy the boundary condition, which means the wave function at x equal to 0 has to be 0. Unlike the full harmonic oscillator problem. So if I ensure that the wave function at x equal to 0 has to be 0, this can only be satisfied if I take on the odd values of n for this particular wave function, as I have written here. Because if I have taken odd values like 1, 3, 5, 7 and so on, then my wave function will already have a x factor in the wave function, and at x equal to 0 my wave function will vanish. So the ground state wave function in this case will actually correspond to n equal to 1, and which will actually ensure the vanishing of the value of the function at x equal to 0, and then it will have a form in the x greater than 0 area, which it will increase and then finally decay exponentially. So this is what I have drawn. It's just a schematic wave function plot I have shown, which basically ensure that the wave function is 0 at x equal to 0, and it increases and then eventually it decays as I go to higher and higher x value. Okay. So this eventually leads us to the ground state energy as well. As I have told that the value of the wave function should satisfy the boundary condition, which is that at x equal to 0 it should be 0, which demands only odd values of n to be taken for this general wave function. So the ground state energy for this problem will correspond to the energy for n equal to 1, which is 3 by 2 h cross omega in this particular case, as opposed to half h cross omega in the full harmonic oscillator problem. Move on. Let us discuss few problems on degeneracy. Okay, and definitely at this point of time you must have understood that degeneracy makes sense if we are mainly talking about the higher dimensional problem. So we'll discuss few more involved three-dimensional potential now. So this is the problem number 4, and this basically is a asymmetric 3D harmonic oscillator potential. So the form of the 3D potential is this: half omega squared x squared plus y squared plus 4z squared. Why I call it asymmetric? Because there is a 4z square term, and what we need to calculate is the ground state energy of the particle and the degeneracy of the state associated with the energy equal to 7 h cross omega. Okay. So let us first calculate the ground state energy. So for this problem, because there is a 4z squared term in the potential, the nth state energy of the particle will look like this. So the x and the y component will give me n plus half h cross omega, but the z component will give me a n plus half 2h cross omega, because it is 2z whole square, which gives me 4z square in the potential. So the most general form of the energy looks like this: nx plus half h cross omega, ny plus half h cross omega, and nz plus half 2h cross omega, which if I simplify will give me a form nx plus ny plus 2nz plus 2h cross omega. Now definitely for the ground state energy, I will substitute nx, ny and nz to be 0, which is the lowest value of n, and which will give me the lowest energy for this problem. And if I substitute nx, ny, nz to be 0 in this expression, I will get 2h cross omega as the ground state energy for this particular problem. Had I had a symmetric, completely symmetric three-dimensional harmonic oscillator potential, well, this particular term would have been 3 by 2h cross omega, but because of the small asymmetry involved, it is 2h cross omega. Now let us calculate the degeneracy, the second problem, which asks the degeneracy of the state with energy equal to 7h cross omega. So as derived in the previous slide, my total energy for this problem looks like this: nx plus ny plus 2nz plus 2h cross omega. And it is given that if the energy, the total energy of the problem is 7h cross omega, then what are the degeneracies I can think of? So I'll evaluate this total energy to be 7h cross omega, which gives me nx plus ny plus 2nz equal to 5. Now there are certain restriction on the values that I will take for nx, ny and nz. So let us fix the value of nz. If I fix nz equal to 0, then nx plus ny will be equal to 5. And in how many ways I can get nx plus ny equal to 5 are these. There are basically 6 possibilities, which will give me the sum to be 5. Okay, so here the bracketed terms which is there 0, 0, 5 and all. The first value here actually is the nz value. So for a given combination 0, 0, 5, here nz is 0, nx is 0 and ny is 5. So the first value is nz and the next two values are nx and ny. And you can see these are the only combinations for nz equal to 0. These are the only 6 combinations which will give me nx plus ny plus 2nz to be equal to 5, which means this corresponds to a degeneracy of 6. Let's move on to the case 2. If I take nz equal to 1, then nx plus ny will be equal to 3, and the total number of degeneracy possible in this case will be 4. If I take the third case where nz is equal to 2, then nx plus ny is equal to 1, which will give me a degeneracy of 2. I cannot have any other cases, because if I take any nz value greater than 2, then this expression nx plus ny plus 2nz equal to 5 will not be satisfied. So these are the only 3 cases where I can evaluate the degeneracy. And I hope you guys will understand that each of these combination, for example in case 1, these 6 combinations, although will give me the same energy value, however the energy eigenstates for all these 6 cases will be different. That's why they are 6-fold degenerate in the first case, 4-fold degenerate in the second case, and 2-fold degenerate in the third case. But we wanted to calculate the total degeneracy of the problem, and the total degeneracy will just be a sum of these 3 cases, which are D1 plus D2 plus D3, which will be 12 in this particular case. As the value of this energy increases, in this case it was 7h cross omega, but as the value of this energy increases, I will have more and more higher fold degenerate states and higher degeneracy for the problem. Okay. All right, moving on. Problem number 5, and this is the last problem in this lecture. So, this is a very interesting problem in the sense that this is of course a 3-dimensional potential well, but just like the problem number 3, I have tried to combine a harmonic oscillator potential with 1D infinite potential well, and wanted to see how the degeneracy and the ground state will evolve in such a combined potential. So, the problem states like this: a 3D confined potential is defined as follows: Vx, Yz is Vx plus Vy plus Vz, and there is a region 0 to L for Z. So, as long as Z lie between 0 to L, my Vxy is a symmetric harmonic oscillator potential, which is half m omega squared x squared plus y squared, and Vz is 0. So, this is in a way you can imagine that within 0 to L value of Z, the xy degrees of freedom of the particle behaves like harmonic oscillator, but Z degrees of freedom is like a infinite potential well, which is 0 inside the box. And for Z less than equal to 0 and Z greater than equal to L, which means outside the region 0 to L, my potential Vxyz is infinite for all values of x and y. So, you can imagine this problem as if it is a harmonic oscillator in xy dimension. However, it is a infinite 1D potential well in the z degrees of freedom. And the question that is being asked is, if L is this pi root h cross by 10 omega, what is the ground state energy in units of h cross omega? What is the degeneracy of the state with energy 12 h cross omega? And what is the degeneracy of the state for a higher energy 22 h cross omega? Okay. So, let us see if we can solve this problem. Okay. So, the first question is, what is the ground state energy in units of h cross omega in this particular case? Okay, because as I said that this problem is basically a combined harmonic oscillator and 1D infinite potential well, where the xy degrees of freedom is basically a harmonic oscillator potential, and the z is like a infinite potential well. So, if I consider nx and ny to be the energy quantum numbers for oscillations along x and y direction, while nz to be the quantum number for movement of the particle along the z direction, then the total energy, which depends on nx and y and z, will be nx plus half h cross omega plus ny plus half h cross omega, because x and y direction it is behaving like a harmonic oscillator. However, in the nz part, in the z direction, because it behaves like a infinite potential well, so it will have the energy of the infinite potential well, which is nz squared pi squared h cross squared by 2m L squared. So, this is my total energy for this problem, which is harmonic oscillator in the x and y and infinite potential well in the z. Now, it is already given that L, if I can write L to be in this form, which will pi squared h cross squared by 2m L square equal to 5 h cross omega. This will actually ease out this problem, because if I substitute the value of pi square h cross square by 2 ml square in the above expression for energy, I will simply get E nx ny nz to be nx plus ny plus 1 plus 5 nz squared h cross omega, which is a much simplified form. And of course, the ground state energy can be calculated from this expression. And as we know that for the harmonic oscillator part, the lowest value of nx and ny are 0. However, for the infinite potential well, the lowest value of n that gives me the ground state energy is nz is equal to 1. So, to calculate the ground state energy in this particular case, I need to choose nx equal to ny equal to 0 and nz to be equal to 1, which will give me the ground state energy to be equal to 6 h cross omega. So, one need to be extremely careful here in choosing the value of nx and y and z. Because you know, the lowest value of these quantum numbers are different in the two problem, the harmonic oscillator problem, the infinite potential well problem, and one should not mix up these lowest value while calculating any, you know, ground state or first excited state energy eigenvalue. Okay. Now, let us look at the degeneracy. What are the possible degeneracies for the first case, which is when E equal to 12 h cross omega. Now, this problem is similar to the previous problem. So, I will just substitute the value of E to be 12 h cross omega and see what kind of equation involving nx, ny and nz I got. So, if I substitute that, then I will get nx plus ny plus 1 plus 5 nz square h cross omega. So, if I substitute the 12 h cross omega here, I will actually get an expression which will involve nx and y and nz. Now, one thing is very important here, because of the term 5 nz squared, there will be a upper limit on the value of nz that I can choose, because my total energy here is 12 h cross omega. So, if nz is equal to 2, so this is just a quick discussion, the energy due to motion along the z direction, as you can see from this expression of E, is 5 nz square h cross omega, right. Now, if nz is equal to 2, if I choose nz to be equal to 2, then my energy, the total energy will become greater than 20 h cross omega. However, the total energy that I have been given in the question is 12 h cross omega. So, nz should not be greater than 1, right. So, nz can take the first value that nz can take is 1, because it belongs to the infinite potential well part. So, if I take nz is equal to 1, then my expression for nx and y will look like nx plus ny plus 6 h cross omega equal to 12 h cross omega, or nx plus ny equal to 6. And this expression nx plus ny equal to 6 gives a total degeneracy of 7, because I can have only 7 possible combination of nx and ny, which will give me the sum to be 6. So, in this particular case, the total degeneracy is 7, because nz can only take value 1, it can't take value 2, because if nz takes a value 2, then the total energy will become greater than 20 h cross omega. Alright, let us move on to the second problem. It is basically the same question. It is being asked to calculate the degeneracy of the state, but with a higher energy, 22 h cross omega. So, again the energy expression looks like this, nx plus ny plus 1 plus 5 nz square h cross omega. And in this case, because 22 h cross omega, which is the total energy given, is greater than 20 h cross omega, hence we need to consider the nz equal to 2 case also, right. We will have two cases, one is with nz equal to 1 and the other is with nz equal to 2. So, if I take case 1, when nz is equal to 1, then nx plus ny is equal to 16, which gives me a degeneracy of 17, and this expression nx plus ny equal to 16 can be calculated from the actual energy expression. And in the case 2, when nz is equal to 2, then nx plus ny is equal to 1, which gives me a degeneracy of 2. So, the total degeneracy in this case will be a sum of these two degeneracies in the two cases, and the total degeneracy here is equal to 19. So, once again in the tutorial sheet that I will give on these topics, I may combine different type of potential well in a given problem. So, you need to carefully write down the total energy expression depending on which direction or which degrees of freedom follows what kind of motion or potential well, and then I'll give different energies and will try to ask you calculate the degeneracy for different problems. And you can actually selectively calculate these degeneracies like the way it is calculated here. I hope I was able to convey the concept of degeneracies in a more elaborated fashion in this lecture, and I hope you will be able to solve the problems that I'll give in the tutorial sheet. I'll stop here. Thank you very much.